Hello students, I am Abhishek Kumar. I have graduated from IIT Kharagpur and I am associated with the askIITians for last 4 years. I am the physics IHE in the askIITians. So today in our first class, we are going to start with the chapter Unit Dimensions and Errors. Now in this chapter, we will first try to study what this physics is, how this study of the physics, the measurements associated with the physics and all of those things started. What were the difficulties that the scientists faced at that time and how they tried to resolve it. The unit that you are using nowadays called SI units, it didn't came up as a unanimous thing in the physical communities. So it had to come up with after many of the difficulties that they faced. So we will study how it developed, how we got the SI units and how now we are using it. So let's begin our class. Today we will start the chapter Units and Measurements. Now the topics that we will be covering in this chapter, units and measurement, will follow in this manner. The first subtopic that we will deal with is the physical quantities and the units. What are physical quantities? How do we describe them? How do we denote them? How do we measure them? And the units used for the measurements of these physical quantities. Then we will deal specifically with the process of the measurement. How do we measure in our daily life? How will we measure when we study in the later chapters measuring of different physical quantities? Then what are the limits to the measurement? When we measure, there are the limits to the measure, the precision, the accuracy with which we measure. What we normally speak in our literal terms, they are actually quite well defined terms here, the limits, accuracy and measurement, that we will see in this part. Then we have significant figures, like when we denote a physical quantity like a force or a mass or a velocity, then we denote them in terms of the magnitude, the scalar quantities. Now how significant those figures are, the way they are measured, they are given, we will deal with that in this subtopic. Then we will deal with the uncertainty in measurement, the uncertainties that we cannot remove in the measurement. We will address those concerns here. Then we will move to the error propagation, where we will see how the error that we take while measuring it manifests in the later measurements. Then we will do the dimensions and the dimensional analysis, that will deal mainly with dealing with the physical quantity only in terms of their units, or which we will later start to call dimension after introducing some new elements to the unit. Then in the end we will deal with the vectors. So let's start the chapter. The first thing that we need to deal with while we are studying physics is the very basic question of what are physical quantities, what are the physical quantities that we are measuring, what are those things. So the physical quantities, all of the things that we measure in our physical life, that are called the physical quantities. Now what this physics does that we are studying, it forms a link between the physical world concepts that are happening all around and the mathematical world, the quantitative part, how we put the things that we observe in our nature all around ourselves in the environment, and how do we put them in a mathematical world in terms of the numbers, in the terms of equations. That is what this physics is going to do. Then we have the quantity in physics then can be measured or quantified. What are the quantities that we can measure? Like we can measure mass. We have been used to seeing the measuring of mass in our grocery stores and all where, and then we can measure the speed with which it is moving. So these quantities in the physics that we measure are quantified, and then we will give a value to it, we will assign a value to it, that we call quantification. Means we give it a value, a scalar value, a magnitude we give it, that's what is called this quantified. We give them a value by after the measurement. Examples are like when we measure the mass, we know we give it the units kg, we have this like 5 kg, 10 kg, something like that. Then we have the amount of substance that we measure in terms of mole. We know all this, we have done this in class 10th. Then we have length that we measure, then we measure time, we measure the temperature, electric current, light intensity, force. There are many physical quantities. All of the things that are happening around us in the physical world are the physical quantities. And how do we measure? We measure by giving them a name, by assigning them a quantification in terms of various units. Now what are the physical quantities, what type of physical quantities are there which have been quantified. There are actually two kinds of the physical quantities that have been quantified by international system of units. What we call now, which you must have seen in your junior classes, that we have been used to saying SI units. These SI units are the units that have been assigned by this body. This body was found by the scientists all over the world to give it a standard value to a particular physical quantity. Like for a mass, we have given kg. So this 1 kg, measurement is same anywhere on the globe, be it in the US or be it in the India. At every place the weight, the mass of this 1 kg thing, whatever it is same. It will measure the same mass if you take it at a different place on the globe. So how to standardize it? Because earlier, as we know, we had many different system of units that were followed by people in their respective localities, in their respective countries. Like you must have heard of pound, you must have heard of inch. So these were the units, this pound and units, these were the units that were used by the Britishers. The Brits used it in for their own measurements. So they were like non-standard. A person sitting in France or a person sitting in India had a totally different set of units for measurement of mass. For mass, here we measure the weight in terms of pound. Then we had in France, we have a different unit system that will measure 1 pound will be something different, and suppose I am taking x units, 1 x will be something else. So it was very difficult for a scientist who is residing in Britain and a scientist who is residing in France to communicate between themselves. So there was felt a need that we should have a standard system of units, an international system of units that would be followed by people all over the world, so that there won't be problem between the scientists communicating between each other, between any discoveries that happen, between any invention that is being made. All of the thing can be quantified in a manner that will be understood in the same manner by each and every people on the earth. And hence this international system of units came into being, and the units that it defined are now called SI units. Now these SI units, they are actually of the two types. They are fundamental and derived. When we say fundamental, we mean these are the basic structures of the units that we will be using, like kg. This is the most basic unit for mass. This is called a fundamental unit. Now, like we know velocity. It has a unit that we know as meter per second. Now the fundamental units, this was for mass, then we have velocity, for length we have meter, for time we have second. Like this we have 7 actually fundamental units. Now if you see a term velocity that we have been used to in class 9th, its unit is meter per second. Now you can see that we can use these two physical quantities, fundamental physical quantities, units, to describe this third physical quantity. So this physical quantity can be derived from these two. So these kind of physical quantities are called derived, and the units that come in are called the derived units. So like this we have 7 fundamental physical quantities that we will see in detail what are those. Now the set of the units which are completely independent of each other, as we talked in this, we have given the 7, we have 7 physical quantities, and this again, this 7 physical quantities, it has been defined by the international system of units. They have defined these basic units which are completely independent, like kg has been independently defined from meter, meter has been independently defined from second. They are not dependent upon each other, they are independent of each other. Now the units from which every other unit can be generated are the fundamental units that we talked. These are called the fundamental units. Because from this unit we can derive any other unit, like we did for velocity. Like suppose you have acceleration. If we have the acceleration, we know the unit for it is meter per second square. So what we have used is, we have used meter, we have taken the unit S is in a square form, and this, by using this two units, these two fundamental units, we have derived a unit physical quantity, that is called a derived physical quantity. Similarly, we know force. If you remember, the unit was kg meter per second square. So here we need the unit of mass, we need the unit of length, then we need the unit of time, and by combining these we can define this third physical quantity, which we will call the derived physical quantity. Now what are these 7 physical quantities that we have been talking? And as we know that this have been defined by the international system of units. So the first most standard system of units that we have been used to in our earlier classes is meter. Now we have been used to using meter for length, but how has it been defined? This is the manner in which it has been defined. It is the distance travelled by light in this second. So if you try to see it, actually the velocity of light, this is actually equal to 299,792,458 meter per second. This is the velocity of light, and actually this is a universal constant. This is a universal constant. What do we mean when we say universal constant? We mean that this constant doesn't change upon changing of environment. Like if you change the pressure, if you change the pressure, temperature, or if you measure in vacuum, or you measure somewhere else, the value, this velocity of light will remain the same. This is same in vacuum. This is velocity of light in vacuum. This will remain the same even if the temperature is 40 degrees Celsius or 30 degrees Celsius, the velocity of light remains the same. If someone measures it from the Mars, or someone measures it from Jupiter, or from someone Earth, everyone will find out that this is the velocity of light. So what they have done is that they have taken this velocity. Now the velocity is unit of meter per second. That means that the light goes this much meter in 1 second. It goes this much meter in 1 second. So it will go 1 meter in 1 by this second. This is how it has been defined. 1 by 299,792,458 second. The time in this time the light will go a distance of 1 meter. Now the second physical quantity that is also quite common is mass, that is kilogram. Its unit is kg. It is the mass of a specific platinum iridium alloy cylinder that has been kept in the International Bureau of Weights and Measures at Severs, France. Now this is a specific, as has been written here, platinum iridium alloy. This is actually alloy. This is a platinum iridium alloy. PTIR alloy. This is like this, a block of platinum iridium alloy. It has been kept here in the Bureau of Weights and Measures, and the mass of the block that is kept at this place in France, this mass is 1 kg. So suppose if a person from India goes there and he wants to measure the mass of his block, and he wants to tell how much is the weight, what he can do is he can take this, he knows this is suppose this is 1 kg, then with respect to this he can measure it, and suppose it is 1.5 kg, he finds that this is 1.5 times heavier, that means its mass is 1.5 kg, and that's how all over the world the mass has been done. Now the third common unit is the second. Now what is this second? How has it been defined? It is this oscillations of cesium atom. Now it will be difficult for me to convey what exactly this means. This is actually the time this many oscillations actually take place in 1 second. Okay, in this many oscillations take place in 1 second. So actually if you try to see it reversely, in 1 second actually 1 by this whole number thing happens, and so from this has been defined, because for a cesium atom, now this oscillation happens when there is a transition of electrons. So it has been taken from there, which is a constant again, it does not changes, that factor has been taken here and used to define time. Now the fourth one is the temperature, and the unit we know is Kelvin. Now the unit we have been used to very commonly using are the degree Celsius and degree Fahrenheit. Now these are not the standard units. Fahrenheit and Celsius, they are not standard units. The standard unit is Kelvin, the SI unit that we call now. This has been defined. This is the fraction of 1 by 273.16 of the thermodynamic temperature of the triple point of water. Now what does it exactly mean? I may not be able to convey this at this point of time in our lecture. What this triple point of water is the temperature at which both the ice, the water and the vapor, all of these three are in equilibrium at this temperature, and this temperature is a constant. Constant, by constant I mean it does not changes with pressure, temperature or anything. Even if you are measuring it in a different temperature, this will still be this. You can measure it and the value will come to be the same. This point is independent of this pressure and temperature. This will always occur at that particular temperature, and from there it has been defined. Now the fourth one is relatively new. This is current, but we have seen this in class 10th. Its unit is ampere. What is ampere? How has it been defined? It is defined by this, that the current that flows with electric charge of 1 coulomb per second. Now if you remember, the current we have was charge flowing per unit time. So 1 coulomb charge, if it flows in 1 second, has been defined as 1 ampere. This is how this has been defined. Now the charge on the electron, we know that is a constant. From there we can get coulomb. We know 1.602 into 10 to the power minus 19 coulomb is the charge on one electron. So one electron has this much charge, 1 coulomb has this much charge. So from there this has been defined. Now the next one that you haven't seen till now is the luminous intensity. And this luminous intensity, to give you a vague idea, you can see it from here, the word luminous. This is for a body that is emitting radiation, like a bulb. Suppose this is a bulb, this is emitting radiations. So this is emitting energy, you can say it, or light. Light is a form of energy. So it is emitting this energy, and so if you have to calculate intensity, means the energy that is falling in a particular area in a unit time, you can find out using this. For this the unit is candela. Now the luminous intensity in a given direction that emits monochromatic radiation. Monochromatic means it's only one radiation, like white light that we see, it has 7 colors. So it's not monochromatic, every color has its wavelength, so it's not monochromatic. So this is a monochromatic radiation whose frequency has been given, clearly a specified frequency which makes it monochromatic, only one frequency, and that has a radiant intensity. It has been defined in terms of intensity. That we will see later what this intensity is, but this is the quantity that you haven't seen, this is a new quantity. Then we reach now at derived quantities. Now we have seen what this derived quantity is. The derived quantities are quantities that have been derived from the fundamental units. Fundamental units are the 7 units that we have defined here. Using these 7 fundamental units, we define the derived quantities. Now we will see how do we define all other. The question here says that how do we define all other physical quantities. We have seen for mass, we have seen for temperature, we have seen for length, we have seen for luminous intensity, for current, everything. Now what about other quantities that we have seen, like velocity, acceleration, force, momentum, all the things that we have seen in our daily life, that we have been used to measuring. How to describe those physical quantities? These are the quantities that are called derived quantities. We actually derive them from the fundamental quantities, the 7 fundamental quantities that we have defined. What we do is that, how do we reach at that? We use an equation that connects the quantity whose units we wish to define with fundamental units. Like suppose I told you what is the unit of force, how to get there. So we know that the formula for the force is mass into acceleration. We have studied this in class 9th. Now the unit of mass is, we know, kg. The unit of acceleration, this is multiplied with this, so the unit of acceleration is meter per second square. So the unit of force is kg meter per second square. This is how we get to the unit of a derived physical quantity. What we do is that we take the units of those quantities that are involved in it, we write for them, and then we get the units for the quantity as a whole. So what we have to do is we have to remember a formula, recall a formula from where we can get to that physical quantities. Now it may be possible, like we know energy. Now someone remembers the formula for potential energy, suppose mgh. Someone else remembers the formula for kinetic energy. Now which way to go and which will be correct? So you don't have to bother about it. Actually, since both are energy, the unit that you will reach to will be the same for both. We can see it here. Mass is kg, g is meter per second square, and then you have height is meter. So the unit that you get is kg, meter into meter is meter square per second square. Now if someone uses this, mass is kg, what is velocity? It is meter per second, and we square this because this is v square. So what you get again is kg meter square per second square. So we will get the same unit for quantities that are same, physical quantities that are same. You can recall any of the equation that you have in mind, and then you can get to the units of it. Now here I have shown the units for acceleration. How to get? Now if you remember, you had an equation like this: s is equal to ut plus half at square. So if acceleration was g, this was half gt square, things like that. When the initial velocity u was 0, we had simply this equation. We have done this in class 9th. So now you have this. If you have to find out the acceleration, this is g. What you have to do is write g in terms, take g on one side. So what will happen? This 2 will go to the numerator, and this t square will come in the denominator. So this is 2s by g square. Now this is what 2s by t square, sorry, this is t square. Now we put, there is no unit for 2, as we know the constants don't have a unit. 1, 2, 3, 4, 1 by 4, 7 by 3, all these are numbers, fractions, they don't have a unit, they are dimensionless or unitless, you can say, at this point of time before we discuss dimension. Now you can put it for s, it is meter, this is time is second, this has been squared, so this is meter per second square. This is the unit for acceleration. This is how we find out the derived quantities. Now these are some of the derived physical quantities that have been derived using the fundamental physical quantity, like the volume we know this is meter cube, this is meter into meter into meter. Meter was the basic fundamental unit that has been used here. Now if you go to density unit, we know it is kg per meter cube. This is the fundamental unit for mass, this is for length. These two physical quantities have been used here to describe this third physical quantity is density. Similarly, speed we know Newton is for the force, kg meter. We have a SI unit also as Newton. Even this is the correct unit. Newton has been given, the name has been given to honor the scientist. So you can use either this or this, both are correct. Then similarly for joule, this is energy, you can write this as the SI units, or this, both are correct. Then you have Pascal, which is for the pressure, its unit is kg by meter second square. So in our last class we studied what are the physical quantities, what were the fundamental quantities that the scientific community defined for their convenience, and the derived quantities, how we got the derived quantities from the fundamental quantities. So in the next chapter that we will do in the next session, we will start with the measurements in the physics. So till then, stay tuned for more of the videos. Thank you.